Hi, everyone. Welcome to our AI Edge seminar series. Today, it's a great pleasure to have one of our own return to Ohio State to give this talk in person. So Xingyu Zhao received his master's degree from Tsinghua University and his PhD from the Ohio State University in 2020, just before the pandemic. He is an assistant professor at Wayne State University. At Ohio State University, Xingyu won the Presidential Fellowship, which is one of our most prestigious awards given to PhD students. And partly the award was given because of his a seminal contribution to load balancing, where he solved the discrete version of the famous Kelly and Lawes load balancing problem. So this had been a problem that had been open for nearly almost 3 decades that Xingyu was able to solve. Xingyu has received various grants from the NSF, and he's also received various best paper awards already, and it's a real pleasure to welcome him here to talk about differentially private federated linear contextual bandwidths. All right, Xingyu.
Okay, thanks for this introduction. Hello, everyone. My name is Xingyu. Today I will talk about our very recent work on differential private federated linear context bandwidths. So let's first lay out the background. So we consider maybe now famous cross-silo federated learning. Take the hospital as an example. We have multiple hospitals. They want to work together to realize this kind of collaborations through the help of a central server. So we have a local model at each hospital, and they will communicate with the central server. The server aggregates model, updates the model, and send back to the agents or silos. And this process will continue for multiple rounds until certain performance is guaranteed. Okay, so that's a quick warm up. And I have a quick note. Oh, sorry. This one. Here.
It'll work.
Oh, so okay. Okay, so I have a quick note here that the difference between the cross.
Speak a little louder.
Okay. There is a slight difference between the cross-device and cross-silo federated learning. So in particular for this talk, we will consider the second one, cross-silo federated learning. And we also have to distinguish between the bench federated learning or online federated learning in this kind of bench setting, right? Or supervised federated learning. So there's a static batch of data at each silo, and basically adopt this offline training. You can send out like cancel diagrams. On the other hand, in this talk, we focus on this federated online learning. Each silo or each agent has a stream of data, and basically it adopts this kind of online learning, or learn from interaction. You can think about the personalized medical care, right? So for example, at time slot T, the bunch of users come to the hospitals. They provide the medical history, the hospital provides action, right, the medicine, and then receive some feedback. And at the next time slot, there's a bunch of new users come to the hospitals to receive the recommendations. And so you may wonder, okay, what is the function for the feedback, right? So it's some kind of reward function on this kind of context, the medical history, and the recommended action, right? So in this talk, we consider the linear context bandwidth. So basically, the function is the f function is a linear function with respect to the feature vector. Here, the xt is the feature vector, which we use the known feature map phi, which maps the context and action to a d-dimension vector. And theta star is the unknown parameter we want to learn. And of course, eta t is the zero domain noise. The performance metric is basically the group regret. Basically, the regret over agents and over time. That's it. Okay. So, although federated learning is proposed to help to resolve the privacy issue in this kind of learning, right? But the locally stored data cannot resolve the privacy issue completely. So we can use, or adversary can use model inversion attack or membership inference attack to still gain the sensitive information of users. For example, the adversary can attack the model updates, can attack the global model. Moreover, other silos agents can work together to try to infer the user in another silo. Okay. There are so many different adversaries. Okay. You can see the hospital 1 and hospital 3 work together to try to get some information of the user in hospital 2. How can we solve this problem, right? So in this talk, we consider maybe the now, maybe a very established tool for addressing the privacy issue is differential privacy. So what is differential privacy, right? We have a differential privacy 101. So we say a mechanism is epsilon delta dp. Basically, it means that the output of the mechanism on two labeling data sets, they are close in probability sense. Okay, you can choose whatever closeness notion you like, but my personal base choice is F divergence, okay, because that is more information theoretical. And there are two key components in the definition of differential privacy. You have to specify what are the input data sets and what are the output. The input data sets basically specify what is the identity you want to protect, because the two labeling data sets basically differ in one single point. Okay. And what are the outputs? So basically, what is the output of the mechanism? So what is the view of the adversary? By observing the outputs of the mechanism, the adversary cannot distinguish which data set you are operating on. Right? There are two key properties we will use in this talk. The one is composition. Basically, you participate in multiple calculations, your privacy loss should add up. And the second one is position. Basically, once you're being private, if you do not touch your original data anymore, you will continue to be private. So based on this kind of knowledge, you may think, well, okay, how about privatizing all the model updates from all the communications time slots from all the agents, right? Then we can defend this adversary, right? Because you privatize the model updates. By post-position, this global model is also private. So you can defend this adversary. Moreover, by post-positioning again, because the receiver data of other silos is also some kind of function of your private model updates. So by post-positioning again, you can defend that kind of adversary. So by resorting this notion of differential privacy, we can address all of this kind of adversary. So that's a motivation for this kind of silo level local differential privacy definition. Roughly speaking, basically means that all the communication from each silo is private. Basically, the full transcript of the communication between any agent I and the server is private. Basically, for any two labeling local data set, you cannot distinguish too much by observing the model updates from that agent. I think it really makes sense, right? So there are two features of this definition. So what's the input? The local dataset here is basically a sequence of T users, right, which could differ by one user. We want to protect the individual, each patient, rather than protecting the identity of the hospital, right? We know which hospital participating in this cross-field learning. That is not privacy, right? We really want to protect the individual patient. So there's a huge difference between cross-silo DP and cross-device DP. So that's the reason why this kind of notion is also considered in this cross-silo supervised field learning. Okay. And what is the output? The output is a full transcript of the communication. What does it mean? It means two aspects. One is the communicated data, model, message. The second one is communication schedule. When you synchronize, when you communication, this is important. Roughly speaking, consider this kind of original output. We have some kind of update at timestamp 1, 5, 10. If you change one user, you should basically keep the same fashion, okay? Same mode update at the same time slots, something like that. If you can preserve this, you are private. Okay. This is our goal. What's the state of art? The state of art is in this Europe's paper. The algorithm basically feeder in UCB. I will talk about this more with Gaussian noise. What is the privacy? Basically, they essentially consider the same privacy as ours. And what is the performance? They say that, okay, the additional regret due to privacy is on this order. It's a root MT over epsilon. The epsilon is the parameter of the differential privacy. And their conclusion is that for this kind of feeder learning setting, with their algorithm, they can manage the regret achieved by a super single agent. What that means? It basically means that there is a single agent who can immediately observe the feedback, right? So that could serve as a benchmark or lower bound for this kind of feeder learning setting. Okay. Basically, they say, okay, the top one with privacy can manage the lower one. Okay, that's the one. Unfortunately, there are two fundamental gaps. We show that the privacy is not valid. They have a fundamental privacy leakage in their algorithm. So basically, the proposal failed to guarantee the zero-level LDP. And actually, we show that a simple type can leakage the user's information. Moreover, the regret is also not well grounded. In fact, there is a miscalculation in the regret. It turns out that the correct regret should be on the order of m to the power 3/4. The m is the number of agents. M is number of agents. So you can see there is a gap, right? There is a gap compared to the lower bound. So their conclusion is not well grounded after this correction. Okay, so that's our motivation. So what are our main results? We first identify the privacy and regret gap in the state of art. And second one, also basically, the key problem with this privacy leakage is that they only protect the communication data. They do not protect this communication schedule. Communication schedule, when the communication happens, could leakage users' information. The second one, we propose a theoretical feeder learning with flexible privacy protocols. And we use this kind of thing to do two things. The first one, we fix the issues in the state of art. We provide the correct privacy guarantee without any privacy leakage, and the correct regret bound, which is on the order of m to the power 3/4. So you can see there is a gap, right? So in order to further close the gap, we consider another notion of differential privacy, which is now very famous, which is a shuffle differential privacy, which is still a weaker trust model. So we do not require the user's patience to trust the central server. We just add a shuffle in between the agents and the.
So this O of tilde simply means that you're suppressing the long.
Yes, exactly. Also, I ignore the dimension. So this just focus on the number of agents and the time slots T. So this is still a weaker trust model. So we add a shuffle between the agents and the server, and we ensure that the input to the server is already private. So we do not require the server to be trustworthy. Okay, it's very suitable for this kind of feeder learning system, right? And under this notion of SDP, we close the gap. That's the main result. So you may wonder what's exactly privacy gap in the SOTA, right? I will show you. Basically, the dynamic communication leaks privacy. As I said before, the communication schedule is not fully private. Observe when the communication happens, the silos can infer the sensitive information. Okay. So let's take a closer look at the communication schedule in the SOTA paper. Basically says that whenever there exists an agent such that a certain functions, this certain condition is satisfied, then a communication is triggered. Then all the silos will synchronize with the server. That is a communication schedule. Basically, for if there exists an agent I such that this condition is satisfied, then all the servers agents will work together to send the model to the server. So the Z is basically all the previous synchronized data. XI is some kind of new data locally collected at each hospital. F is just some kind of function. I think based on this, you already see some problem, right? So suppose in this case, the hospital 1 triggers this kind of communication, and then all the hospital send the mod update to the server, and server send back. Now the problem comes. So malicious silo can take advantage of this kind of thing to infer user sensitive information in another silo. Here is a simple toy example attack. So let's consider a very simple case. Just at time slot 1, Alice and Bob come to 2 hospitals.
Yeah, just a
Oh, sure.
question. So it seems this kind of leakage could be due to this thing synchronization. Everything update now.
Yes.
So what about these updates are asynchronous?
Oh yeah, good question. Yeah, that's actually that's one thing we are currently thinking about. But for the asynchronous, even the regret analysis is a little bit tricky because you have to deal with a well-constructed filtration to apply the self-normalizing quality. So that is very technical, but we can talk about that offline. Yes. Good question. Yeah. Okay. So let's come back to this kind of synchronous. This is the synchronous feeder learning. Of course, there is the asynchronous feeder learning. Yeah, but let's consider the asynchronous feeder learning. So whenever one agent wants to communicate, all the agents should participate in the communications. Okay. So now at time slot 1, Alice comes to hospital 1, Bob comes to hospital 2. They interact with the hospital, and they send the information, get the feedback. And suppose hospital 1 satisfies the condition to communicate, and then both of them will communicate. On the other hand, hospital 2 does not satisfy the condition. Okay, so in this case, the communication is triggered by hospital 1. And then save this. Now problem comes in. We immediately have some kind of privacy leakage of Alice. Why? The Silo 2 can infer Alice data. How? Silo 2 observes some kind of new data comes from the server. And Silo 2 itself knows that this synchronization is not triggered by itself, right? Hence, it must due to the hospital 1. Okay. And moreover, the F function is a public law. So he can recalculate, re-engineer the xi, the x Alice, right? Because Silo 2 knows that f x Alice and z not than 0. And he knows the function form of f. So he can know something about x Alice, the feature vector of Alice. What exactly the information of Alice can be inferred? Let's take a closer look, right?
But I thought XI was non-private data.
Yes.
So then what does it matter if Bob knows the non-private data?
Oh, by non-private data, I mean, non-private data basically some sensitive data you haven't privatized it yet. Just like the medical history.
I see.
Yeah. Just like the HI86 or some kind of medical history. By non-private data, I mean, you haven't yet privatized data before you send out. Just some kind of locally sensitive non-private data. That is, it's not mean non-sensitive. You may that data is still important.
I see.
It's not the non-sensitive, right? It's still sensitive, but it has not been privatized yet.
Yeah, so I'm just wondering if you have more than 2, then you cannot you can infer that okay, there is some attack, but you cannot infer.
You can work together.
Okay, so you are saying the multiple address.
Yes, that is the law, right? In differential you cannot assume any setting information of others, right? Basically, information will DPC will basically protect all the setting information. As I said, hospital 1, 2, 3, 4 can work together to try to infer the hospital 5. Right? Yes. But this is just a toy example. So, okay, with hospital 2 knows that if X is Z not than 0. So in order to figure out what exact information of Alice can be inferred, right? Let's take a closer look of the function form of F. What is the rule, right? What is the rule behind this kind of communication? What is the function you should calculate before you trigger this communication? It's just a famous determining trick. This kind of formula actually has a physical meaning, basically just local cumulative drift. Okay, but I will not touch upon that. Basically, just some function, and the T prime is the most synchronized time slot before time slot T. So in this case, the T prime is just 0, and T is just equal to 1. We know that hospital 2 knows that this condition is satisfied at time slot 1. And then he plugs in the function form, and he directly knows that the norm of Alice, the norm of the feature vector of Alice is larger than a threshold, then that could be a very serious problem, right? So if you use some kind of one-hot encoding, maybe this threshold is basically can tell you that, okay, this guy maybe have many diseases, right? So that is the context information, right? Because the feature vector includes the context information. Okay, I think this convinces you that there indeed exists a privacy leak. So what about the regret? The regret here basically due to the miscalculated total privacy noise. We know that for sure, larger privacy noise imply larger regret or worse performance. Let's first ignore the privacy issue, right? Let's assume that they are correct for now. The total amount of privacy noise in the SOTA paper needs to be corrected. So basically, you have to basically add M factor in front of this current one. So accounting for this, then your regret change from this kind of root MT to M to a power 3 factor, because you add M factor in front of the noise. Okay. So we have a gap compared to LoBa. So a short summary, for privacy, we have the privacy leakage due to this kind of adaptive communication. For regret, we have this kind of gap compared to a LoBa due to its M factor noise. So what are the motivating questions we would ask? First, how to address the privacy leakage? Right? Maybe a natural problem or natural approach to think about it is just, okay, let's consider fixed bench scale, right? Which does not depend on the non-private data or non-sensitive, the sensitive data. We just maybe every 5 time slots we communicate. That is fixed bench schedule, right? How to correct the regret bound while preserving the privacy. How to close the gap compared to the LoBa. We need a way to get rid of this kind of addition M factor. Moreover, if possible, can we have a generic analysis or generic algorithm, right? We just plug in and then we get a result. We do not have to analyze, have different analysis for different notions of privacy. We need a template proof, maybe one-line proof. So here is our approach. So we first propose a generic algorithm, which is called private failure in UCB. Basically, it's just like a fixed bench synchronization of the single agent in UCB with privacy protection. So let's first have a very quick warm-up of the single agent in UCB, right? So basically, it's just online learning. For every time slot T, you have 2 steps. First, estimate the unknown parameter, use region list regression. You have the occurrence matrix, you have the bias vector, and then you take the action following the UCB. Okay, the beta T is basically chosen via some kind of common response. XT is the feature vector. Okay, very simple, right? That's maybe one of the state of art for the min UCB, right? Let's adapt this one to repeated learning. Of course, we have to introduce the bench for communication. So every 5 time slots we would like to communicate, right? And we also have to introduce a privacy protocol for the privacy protection. So we initialize some kind of counters. Basically, the WIUI is some kind of local counter to accumulate the new local covariance matrix and the bias vector. And the tutor, the W synchronize or U synchronize basically used for to store this kind of synchronized data, which is private. So we use the tutors for the privacy. Here is some kind of notes. Basically, for each time slot T, for each agent, you first collect all the available data, include the regularizer, previous synchronized data, and your new data. Bias, covariance matrix. Estimate, local estimate, have a local estimate of this kind of unknown parameter. Take the action, following UCB, all the reward. And then construct your new local data, covariance matrix, bias vector. Very simple, right? And then every B time slot, you communicate. Basically, for now, let's think about this kind of P like a black box protocol, just construct, which consists of this kind of local randomizer at the local side at each local agent, and the shuffler or maybe just identity mapping between the agents and the analyzer, and some kind of between the agent and the server, and there is an analyzer at the server. You can think about just a black box privacy protocol for summation. Okay, because really what we did here is for freight learning, we just take the summation over the parameters, the local data. And after you do this kind of synchronization, you send this kind of private version of this kind of synchronized data back to each agent. And of course, each agent should remember reset the counter, right? So that you can accumulate the new data for the next batch. Right? Basically, you use this counter to accumulate the data for the next batch. That's the reason. Okay, great.
So in these additional, in the template protocol,
Yeah.
can you guys also consider compression?
Oh, yeah, that's it. Yeah, that's also, not for this paper, but for another paper, we was trying to consider the compression like quantization, something like that. Yeah, yes. Good point, yes. Remarks are ready. So the key difference compared to our proposed algorithm with the SOTA paper is that we consider fixed bench schedule rather than adaptive bench schedule. Now, because of this kind of fixed bench schedule, it now suffice to privatize the data only without worry about in this kind of privacy leakage in this kind of schedule, right? Because it's independent of the data. Of course, the bench size need to be chosen carefully to balance between the privacy, regret, and communication cost, right? That's a key thing. I want to be more specific of the problem of SOTA. It's not about the adaptivity in the communication schedule. It's about the adaptivity based on the non-private data, based on the sensitive data. Okay. You may think, well, okay, let's first privatizing the data and then use it for the adaptive communication schedule. Then it definitely private because you use private data for the decision, you are private. But we show that it will lead a fundamental challenge in the regret analysis. So that's the reason why we choose this kind of fixed bench schedule. Okay, as I mentioned before, there is a black box privacy protocol, right? In order to understand this, we have a different privacy 201. The first thing we want to learn is Gaussian mechanism, which is calculate the sum privately. You have a bunch of vectors bounded in L2 norm. How can you calculate the sum in a private way? You just add a Gaussian noise. The variance of the noise is scaled with respect to the norm of the vector. Basically, change one data, the L2 changes only in L. So sensitivity, that is sensitivity. Okay. This is not enough because in online learning, the key difference for all the supervised learning, just one shot, right? You just take the non-private data, take it, add one noise, you are done. But for the online learning, we have to update the model, update this kind of estimation, update this kind of summation or average every time step, right? There must be a problem, right? In particular, we have a stream of data. You can gamma 1, gamma 2. You can think about just bits. And we want to calculate the prefix sum at each time step k from 1, 2, 3, 4, every time step. You want to release this kind of continuous private sum. What is how to do it, right? How to do it? The first one, basically, you add the noise to each data. You have one bit. You have a new bit. You first add the noise to that bit and add that bit to the previous. This is definitely private because you add a private thing, right? But the problem is that you add a k noise, right? Because in the end you have added k noise because the last calculation summation from 1 to bigger k in that summation you have k noise mess up, cannot have a good utility. The second one, how about okay? I first take the summation for each prefix sum and add one noise. That is the one is total noise is good, right? Basically, for each summation, you just add one noise. The utility is good, but the privacy is not good because the first data participate in k calculations. The first bit calculates in k calculations, right? So basically, you have to add your privacy loss up. So in order to have this kind of epsilon delta dp, you have to scale your noise, right? So actually, the same noise, not helpful. Yeah, it's not helpful. Now we come to a very smart way. Actually, I like this algorithm very much. This so-called famous tree-based algorithm. I like it very much. It's very smart. Instead of add the noise to single data or add the noise to the prefix sum, we add the noise to the partial sum. This is very smart. So what is the partial sum? We construct a binary tree. Now, you can see the internal node is some kind of summation of the leaf node. We add noise to each this tree node. Key observations. 1, you change one data leaf node, it will only affect log k tree nodes, right? For example, you change gamma 2, it only affects this 4 nodes, all the log k. This sensitivity is bound. You change one data, it will not populate in k calculation. It's just populated in log k calculations. Smart, right? Second one, if you want to calculate the prefix sum, you can say you only need log k partial sum, right? For example, you want to calculate a summation from 1 to 7, you only need 3 nodes. So both orders are log k. So this is famous. I think this is very useful intuition, right? Whenever you have 1k, k1, then you want to construct some log k. Right? So this is very useful. I think this strategy is actually used everywhere, not only in this kind of tree-based algorithm for some kind of low bounding proof. You can also have this kind of binary tree to construct a log k balance. This is very useful. I like it. So ignore all the log k factors. Basically, you still preserve this kind of one noise. Moreover, you can calculate this kind of private prefix sum in a sequential way. So when gamma 1 comes in, you calculate this tree node, private. Basically, you add the non-private data and add one noise. And gamma 2, you will calculate this tree node. So when gamma 3 comes in, because we have a stream of data, right? You have to do this in a sequential way. When gamma 3 comes in, you will calculate this tree node. Gamma 4, this one, gamma 5, this one, and so on. Very nice, right? We can actually implement in just 3 to 4 lines. First, express the time slot k in a binary form. For example, for k equal to 6, it is 110. And you first find the index of the first one. In this case, index is ik is equal to 1. And then you calculate the non-prefix sum. Basically, it's gamma 5 plus gamma 6. This is non-private. Right? For this node, you only need gamma 5 and gamma 6. And then you add one noise. And when you calculate prefix sum from 1 to 6, you only need 2 partial sum, 1 to 4 and 5 to 6. You are done, right? So for
This tree has to be balanced.
oh, you have to do this kind of thing. Yeah.
I mean, the tree can be unbalanced. So if the tree is unbalanced, meaning that a one path on the leaf is pretty longer, much longer than some other path from the
But I think it is automatically balanced. Right?
Can you repeat the question for the?
Oh, sorry. Yeah, I think Kevin's question is about what about the battery tree is not balanced?
No, I'm just asking, do we require this tree to be balanced? So if this tree has to be balanced, then the size of the tree has to be some power of 2. So
Oh, great. So I think it's just some kind of integer issue, right? But I think that it will not be an issue. You mean just some kind of power of 2?
So actually, let me rephrase my question. So if you want to do this kind of efficient processing, are you required to have a balanced binary tree like this, or the tree can be somewhat arbitrary?
I think we do not actually construct this tree, right? This tree is just for illustration. We actually can calculate sum using this kind of code, right? So you just you can say we do not calculate we do not calculate this node, right? We only calculate some part of this node. You can simulate this just by the tree, but we do not actually calculate each tree node in the tree, right?
So you mean as long as you follow this procedure, then that implies a tree?
Yeah, exactly. That's also the point I want to mention. Thanks. So we do not actually formally construct the tree before your calculation. You just imply it by your calculation. Yes. This is very nice. Okay. Now, basically, our protocol basically a distributed version of this kind of classical tree-based algorithm. What can we do? We have 3 paths: R, S, and A. Local randomizer, shuffler, and analyzer at the server. For the randomizer at the local agent, we just copy the first 4 lines to the local randomizer. Okay. We just calculate this kind of P sum. So for each local agent, we just calculate the P sum. Okay. and the shuffler just shuffler, or identity mapping just very simple. The analyzer, basically, we just take the aggregation from all the agents of all the P sums, and then you just use this kind of binary summation to calculate this kind of prefix sum. Okay, so we have this kind of two pieces of things, right? We have an algorithm, we have a protocol. We want to putting them together. Okay. The only missing part here is that we have to use two of this privacy protocol, one for the summation of this covariance matrix, one for the summation of the bias vector. Right? In particular, here, each gamma k is a batch of data. It's a batch of data. So basically we treat this batch of data like a single point, and we insert that one into the tree-based algorithm. So let's see a concrete illustration, right? You may get lost at this moment. We have 3 hospitals. They want to follow our algorithm and our privacy protocol. Let's consider one particular communications time slot, the 6 times. Right? For each hospital, they construct this kind of new batch of data, new local data, gamma 6. Let's focus on this kind of bias vector. The similarity go for the covariance matrix. Okay, we have the gamma 6. Okay, which just corresponding to this the latest batch of data. We have a tree. Right? We have a tree at agents and the server. The gamma 6 comes in. What load we should calculate? This load, right? This load. I calculate using the tree-based algorithm via the local randomizer. And I send to the server. Server aggregate. First aggregate, basically summation over the agents. This is first step. And then we have this kind of aggregate P sum. And then we take the summation over time to have this kind of prefix sum. So basically that's 2 sums. Over the agents, over the time. Then you have this one. You may wonder, how about let's take the summation over the time at each local agent, and then the server only take the summation over the agents. So it's just a simple aggregation. A natural choice, right? How about this? How about take the summation over each agent? Let's do this. It's called alternative one. Data comes in, we have this node, but each agent do this kind of summation over time. 1 to 6. We communicate this kind of prefix sum rather than P sum. Aggregate. And this one is basically the same one as before, right? So you may wonder, okay, what's the difference? Why do we consider your one rather than this one, right? For the 0 level LDP, that is it. Same regulated same privacy counting. But for the sharp DP, our protocol will continue to work to close the gap, but this alternative one will fail. I will talk about this more. Very interesting. This is very interesting observation. Okay.
So here, if you have 2 hospitals, A and B, and the communication from B fails, and you get this response, wouldn't you know at least that hospital A has sent something to the server?
Oh, you mean, or what do you mean?
You know, I was going back to your Alice and Bob example, right? So in the Alice and Bob example, I thought that the communication from Bob failed or whatever, right? Was not able
not fail. Basically, that communication, that condition is not satisfied by Bob. Basically, Bob will not trigger this one of communication. That is triggered by Alice. That is not mean communication failed. It means that communication is not triggered by Bob. It is triggered by hospital 1. So
okay, but here too, let's say you have hospital A and hospital B. You cannot have a situation where hospital B's condition is not triggered.
Oh, you can, right? You can. So suppose in this case, it is triggered by hospital A, right? Right. And then you just communicated this kind of stuff. Right?
But then B will at least know that hospital A communicated. Right?
Yeah, but this kind of communication is not all the send message is already private.
Okay, I guess.
And also this kind of when the communication happens, it does not depend on non-private data, right? It's just independent of data. Right?
But I guess the point that I'm trying to make is that, but B still knows that A communicated. I thought that even that information was sensitive. Right? B will still know that A communicated, right?
Yeah, but no, this is not trigger one. This is every time, every 5 times loss, all the agents will communicate. It is not triggered by anyone, right? Just everyone follow the same protocol. It does not depend on data. Right?
But if that's the case, then there will be some overhead.
Yeah. I will talk about that.
Right?
Yeah,
Right.
communication. Yeah.
Okay. Yeah,
Yes,
okay.
that's a trigger. Yeah. Clear. Yeah. So what are the theoretical results? Okay. We have a algorithm, we have a protocol, right? So for the first part, we consider zero level ADP, basically the same notion as the state of art paper. We fix the issue, okay, because we have a fixed bench schedule independent of data. So with the proper, of course, you get that the choice of the bench size should be root T, right? So with the proper choice of a bench size of noise, we have the privacy guarantee for any epsilon and delta, okay, with a range. And we have the regret, of course, in terms of M, it is M to the power 3/4. Okay. And we have root MT communication. Okay. So compared to the SOTA paper, we fix the privacy. We initialize the correct regret. And the communication part actually, the claim communication in the SOTA paper is log T, but I still have some doubt about the log T. But anyway, because they have this kind of privacy leakage, so that's okay. Yeah. Or compared to the single agent lower bound, we have a gap, right? We have an M to the power of 1/4 gap. So our actual question, how to close the gap? We consider
What is D? Remind me again.
D dimension, feature vector dimension. Okay. Yeah, we just ignore the D here for this talk. Sorry. So then we consider the shuffle differential privacy, and we match the level. So you may wonder what is shuffle differential privacy, right? Let's take a this differential privacy 501. This is some kind of advanced graduate level course. So what is shuffle differential privacy? So basically, we have a shuffler, and basically it means that the output of shuffler should be private. I only care about the output of shuffler, or equivalent input of the analyzer. So how to achieve it? It turns out there is a very simple way. You can see that there is a randomization in the shuffler, right? That could help to amplify the privacy guarantee, because there is additional randomness. So one way to do it is just like LDP amplification. So suppose the output of each local randomizer is epsilon naught dp. Then after the shuffling, the view or the output of the shuffling is automatically epsilon naught over square of n dp. Basically amplification by a factor of 1 over square of n, the number of data points. Great, right? This is great. The intuition also very great, very nice. Basically hiding among the clothes. This intuition can be used to understand the results. Actually, the intuition is used to prove the results. So you may wonder, okay, let's directly add a shuffler between the agents and the server, then we can realize this kind of 1 over square of M application, because there are M agents participate in the shuffler. Then the data point is order of M. So you can amplify by the order of 1 over square of M. With this kind of amplification, good news is that, okay, we're done. We can close the gap because we reduce the noise, right? Because we amplify the privacy guarantee, so you can inject less noise. So you can get rid of the additional M factor. You can close the gap. But the bad news is that we cannot use all of the existing SDP amplification results. Why? All the existing amplification lemma requires that the local randomizer here R only operates on a single data point. That is the traditional definition of local differential privacy. Basically, the local data set has only one single data point. Okay. But here, in our case, all local randomizer basically is a Gaussian mechanism, right? You have a summation over some data points and add a noise. You will calculate the P sum. That is not a single data point, right? It's not a single covariance matrix. It's not a single bias vector. It's a batch of bias vector, and then you take the non-private sum and add the noise. So your non-private data set is not a single one. You may think, oh, who cares, right? This really leads to a key difference in the answers. Okay. Or more intuition here is that clones are become very harder to create. You can say that it's very difficult for you to handle among clones because the clones are harder to create. We derive a new amplification lemma tailored to this kind of Gaussian DP mechanism, and we try to avoid group privacy, and we control the blow up in data. So those are very technical, but actually the intuition is very nice, and we can talk it offline. So with this kind of amplification, new amplification lemma, as I promised, we can reduce this kind of variance by 1 over m, right? Because we have 1 over square of m amplification, so the variance of noise is just 1 over m. And then we have the right order of the regret, and we have minimal algorithm modification compared to the previous zero level ADP. You just change the noise, add a shuffler, done. Okay, very simple, right? You change the noise, add a shuffler, you have automatically have this one. But the problem here is that you can say the privacy guarantee only holds for very small range of epsilon, right? That is very small. You know, for practical use case, the epsilon should be on the order of maybe 1 or 5 or 0.5, something like that. This one could be very small, right? Very close to the other. It's not practical, right? Not that practical. So how to improve the privacy guarantee so that it holds for a wide range of epsilon? Let's leverage this kind of vector summation protocol. Another way to achieve SDP. Another totally different view of the SDP. So instead of using this kind of LDP application, we can use the specific shuffle protocol. Basically, suppose you have n vectors with L2 norm bounded by L. You want to calculate the summation of this vector under this kind of shuffle differential parity model. How can you do it? There is a specific mechanism for it, and it is called a P-wave. Okay, I will not talk about the details. I have a backup.
Because it's a graduate level class, now it becomes differential privacy 5 or 6.
Yes. This is graduate level. Yeah,
Nice.
you get it. Yeah. Yes. Yeah. I pay special attention to that number. Yes. Okay. So this P-wave can guarantee SDP for a wide range of epsilon and delta, and more importantly, I like to view this kind of P-wave sum like it essentially similar central model without a trust server. So basically, in the central model, the amount of noise you add is almost the same order, right? Basically 1 over epsilon square scale with the L2 noise. Basically, this mechanism enables you to calculate the private sum without a trusted single server under this kind of SDP. So this view of this kind of mechanism will help a lot. So basically, whenever you have a central model and you do not want you want to translate it to a shuffle model, you just use this P-wave sum. That will help you. That will help you directly get rid of this kind of trusted server. Now, how can we use this one, right? Can we simply use this kind of P-wave sum to add some bunch of data with a single noise while without requiring a trusted server to our case? So in our case, we want to add the P sum across M agents. Just M, you can think of M data. And can we apply this kind of P-wave sum over this M data, right? M number of data. But there is subtlety. The norm of each data point in our case could be linear with respect to T. You can say the norm is L squared. If your norm is linear with respect to T, your number of the total noise is messed up. Why? Because we just want to do sum of M P sum. What is the P sum? P sum, think about that P sum. That P sum basically is all the points, right? That norm of that the norm of that data, the norm of that P sum is linear with respect to T, right? So this view is in a different way. The problem solved. So let's view this kind of N we want to determine the n. The n in the p-weak sum as all the data points across all the agents. So for the k equal to 6, each p sum has 2 batch of data points, 2b, and we have m 2b, right? The small n is equal to m times 2b. We can apply this p-weak sum to n of the points. So the n now is all the single data points. Yeah? The data set in this case is a single data points of a single bias vector, single covariance matrix. Norm is bounded. So we can add one single noise. Let's see a concrete illustration. So this again consider the 6-time communication. For this kind of gamma 6, right? For when gamma 6 comes in, we want to calculate the kind of p sum of 5 and 6. Basically, the summation of gamma 5 and gamma 6. We know that each gamma 5 and gamma 6 is a bunch of single data points, right? A bunch of data. Right? Okay, they are used to calculate that p sum. Similarly, we have all of this kind of bunch of data. We lay out all of this kind of single data point. So this is n. We apply the p-weak sum for this data set. Each single data point is bounded. The noise is just one over epsilon, single noise. Okay. Okay. So now we calculate this kind of aggregated one, and then we summation over time. We have it. Right? So the p-weak sum allows us to calculate the summation over agents, and then we summation over time. Then we have this kind of thing. And of course, we with this kind of thing, we have the right order. Notably that we have the privacy guarantee hold for a wide range of privacy parameters. That is the gain of this mechanism. But also, we also have to sacrifice something. Because the algorithm becomes kind of complicated, and moreover, you have to store all the data, right? Because you have to expand all the kind of p sum into a single data point. You have to store all the data. So it's not that efficient when we actually implement this kind of simulation. It takes a lot of time to run this algorithm because you have to store all the data.
Plus, you have, I think you also have the communication overhead.
Yes, that's it. But this p-weak sum has some kind of strategy to decrease the communication cost. Yeah. So, and I really want to show the analysis. Okay, I want to be quick here that we say that as long as the black box privacy protocol injects some noise which satisfies some condition, then we can give a generic or regret bound for this algorithm. So basically, it says that, let's forget about all the notation. Basically, says that the noise across time and across agents is sub-Gaussian, and each coordinate has some kind of variance, right? And the variance be bounded. Basically, the total noise is at most sigma total. Then we have this kind of generic or regret bound under the PNC. We have 3 terms. The first term is due to the batching because you update this model to communicate every batch of time slots, right? You are not communicating every time slot. So you have to sacrifice something. That is the cost due to batching. The second one is just standard regret, d root t. And the third one is the cost due to privacy. So in order to have a regret bound, all you need to do is to determine the total amount of noise you inject throughout this process. Then you are done. You just plug into this regret bound. So let's see, how can we easily calculate the total noise in all of the 3 algorithms? Let's first consider zero-level LDP. As a property of this kind of battery tree algorithm, we know that each p sum only injects roughly 1 noise. And we have m agents, summation over m agents. We have m noise. And for summation over time, we just log k, right? We ignore the log k, is still m noise. And then we plug back to our proposition 1, we have this. Now, the second one, basically amplification, you can reduce your noise by a factor of 1 over m, right? The variance. And then you take the summation, now it's just 1 noise. And you take a summation over time, just log k, you ignore the log k, is still 1 noise. And you plug in back to the proposition 1, you have this kind of root empty. Now let's see our p-weak. for each summation of this kind of p sums, right, across the agents, it's just one noise. And you take the summation over log k, it's just still one noise. And then you have this kind of regret root empty. Yeah. Now I want to mention that why I say that we mentioned that there is an alternative one, right, for this kind of privacy protocol. So the key to the success of protocol is that we communicate the p sum rather than prefix sum. This is a key difference because if you communicate the p sum, each data point, single data point, only participate in log k shuffling, right? Okay, because each data point only participate in log k shuffling. Then you use the computation, you only sacrifice log k. But on the other hand, if you communicate this kind of prefix sum, then you think about the first data point. You think about the first data point. It will communicate or participate in root k, right? Roughly a polynomial of k number of shuffling. So you have to compensate that using computation. You have to add a much larger noise, not a local order. It's a polynomial order. You are done, right? You cannot achieve the optimal regret. That's the key. That's the key. I will skip the simulations. I have some discussions. So you may wonder, okay, can we further reduce the communication cost to log t? It's very tricky. It's very tricky. So not only the regret, actually the communication part due to this kind of noise, that one is very tricky. Okay. How about some kind of connection between your our definition of this kind of serial level DP, sharp DP with standard single agent DP notions for context bandits? Right? We give a comprehensive discussion on the difference and connection in the paper. What if users even do not trust each local agent, right? So in our paper, we assume that each local patient will trust the local hospital by sending her non-private data to the hospital. In fact, it turns out a simple tweak of algorithm can even handle this situation. So the adversary could be even the patients within the same hospital. We can handle it. So what if a user participating multiple times? He could visit the same hospital multiple times, or he could visit different hospitals. You can use composition, you can use group privacy, you can also directly analyze the sensitivity. Change one data, what is the total change? How to balance between privacy and algorithm complexity. We have two algorithms, each of them has some kind of ranging. We are right now working on. Can we generate to further reinforcement? I very like your question. Actually, yes, for linear functional approximation, it can be easily done. Maybe just very straightforward. So okay, one last thing. Here's the overview of this kind of private online learning. Okay, so on the left-hand side, you have this kind of different online learning models like bandits, reinforced learning, and you have different function class for the bandits and reinforced learning. On the right-hand side, you have different notion of DP, central, local, and distributed, like the shuffle. And in between, I show that what are the things you need to protect. Okay, so this is somehow a big picture of this kind of private online learning. And based on this big picture, we have done something. So for the private multi-bandits, we have the first lower bound with Wimble and Kevin. We have that paper. So we also have the state of art for the private multi-bandit for all the three models. And for the context bandits, we have the shuffle model, we have the faded learning, we have the curl bandits, and some kind of distributed one. And for the reinforced learning, we also have this kind of the first comprehensive study of the tabular reinforced learning, and also linear functional reinforced learning, and also some kind of LQR. So yeah, I think there are many more interesting problems in this area. Collaborations are welcome. Here is the reference. Thank you. That's all.
We have time for a couple of quick questions.
So one question that I have, you were doing something with peak time, after peak time interval, you are now communicating, right? So how do you ensure that in this peak time, you may have multiple kind of this kind of update, right? So if there is only so that example of Alice and Bob, if we know that, okay, only Ali, if there is some kind of communication, and we know that only Alice's model is being updated, then I can again create some kind of privacy leakage, right? If you are, I mean, in short, like if you are communicating too often, I can guarantee that, okay, there is some kind of at most one kind of update and you can have some kind of privacy leakage.
I may not fully get your question. So, because in our case, whenever you want to communicate, all the agents will communicate, right? So you cannot.
Yeah, but supposing that if I'm communicating too often, right? So then we know that, okay.
Oh, we already account for that. We use we use this kind of composition over the tree, right? Right. Yeah, that is composition, right? We already, of course, if you communicate too often, you have to use this kind of composition over this kind of how many communication you happen. But we already handle that using the tree-based algorithm. Okay. Yeah. Because this can continue private stuff, right? So we already handle that. It's just not okay. Just not okay. Yeah.
Going once, going twice. Anyone from Zoom? All right, thanks again, Shinju.
Thank you.